Okay. So I must say, this has been extremely stimulating week for me. And I thought what I was going to do is to just, after this panel, like my task is very easy, summary of the current status, and then some new directions and reaching out to other communities. It turns out that these topics are exactly what was emphasized in the panel that we just heard about. And the first is really, can quantum gravity be tested today? So this is one of the things. And then some promising paths, which are more theoretical. Good. So summary of the current status. Let me just make sure that, yeah, that's correct. Okay. So LQG community has been engaged in a truly ambitious undertaking. General relativity, when Einstein formulated it, required a new syntax to describe all of classical physics, and that new syntax was given by the pseudo-Riemannian geometry. And now we are venturing to go beyond Einstein by creating a deeper syntax, and this was emphasized by Laura about quantum Riemannian geometry in the area gap. For this, one had to lift the anchor that has tied physics to a smooth space-time continuum since the days of Aristotle, and hundreds of researchers in LQG chose to abandon this comfort zone and venture forth and toil together to make this courageous leap. And it really is a privilege to be part of this great adventure. Now, over this week, we heard advances made in very diverse fronts, and many of them, some of them were discussed already in the panels. First is foundations and mathematical issues. We are really seeing extremely sophisticated concepts and astute mathematical techniques being developed to sort of fit with the new concepts. Then computational infrastructure, then applications of two types, particularly to black holes and to LQC, and conceptual issues and bridge to observations. And of course, the many clear and stimulating talks in the parallel sessions covered these topics and also sort of went into different directions, different shorts, different insights, fresh insights. And for me, really, this last week has been extremely stimulating. I'm also very tired because of that, concentrating so much on these beautiful ideas that are coming in and exploding. And I'm the oldest person in the room, I think, but I really felt that I was a kid in the candy shop, right? So many beautiful things, right? So much stuff. God, completely wonderstruck by that. So both in plenary and parallel session, I really felt like that. And I do not have time to share with you the numerous reasons why I've been so happy and excited throughout the last week. But I'll comment just on a couple of talks, or 2 or 3 talks. And that is because really these talks are making bridges to other communities, and younger people might not have captured that. And the first comment I want to make is really Thomas Tiemann's talk. Thomas has been a bastion of background independence, and therefore I think many in this room were a little bit taken aback by the fact that he was proposing to abandon background independence and introduce background fields and do quantum gravity along that lines. But I think one has to sort of understand what his motivation is. His motivation is really to make contact, precisely reaching out, make contact with standard quantum field theories. And particularly, he was looking at asymptotic safety and the functional renormalization group there, where everything is done by introducing a certain background up here. And I think that this is sort of a very nice adventure. This is not only adventure, but there's a very nice initiative in which, the beginning is not a long thing, because we have to learn in detail. We can't just say, oh, they have a continuum, which they have, and we have a discrete geometry, we have area gap, we have a built-in ultraviolet cutoff. But I think we have to sort of see nitty-gritty of where things are different. And already what Thomas reported, there was one big signal, namely that he tried to do all these things, the functional renormalization group, using, and also Renata's talk in a parallel session, functional renormalization group, using the connection variables, but he could not do it, and so he went back to the metric in the extrinsic curvature. The discreteness of quantum geometry comes naturally from the holonomy flux algebra. background independence, and holonomy and flux algebra leads to discreteness. And somehow that had to be abandoned in order to make contact with ordinary quantum field theory. It tells us something. And I think, we're going to learn more and more as to which things those people are missing out, but in a concrete manner, not in sort of just in general knowledge. And the other two talks that I would like to sort of comment upon, again, making bridges to other disciplines, are the talks by Eugenia and by Beatrice. I mean, Eugenia's talk has given us a very, rather pristine framework which generalizes the topological quantum field theories. And it is really quite well tailored. It needs a crucial ingredient, and that ingredient is this transition amplitudes, I feel like this path integral that she is talking about. But she doesn't have it's a framework, right? It's not a theory. It's a framework, so somebody has to give her this path integral, and then she can draw some conclusions from it, and interesting conclusions from it. And at the moment, of course, nobody, no other approach other than people working in this room have a possibility to give her the ingredient, which is just amplitudes. Using spin form and your group field theory, I think we can really make it complementary to what she was doing and sort of make really connections to all these, the outside world, so to say, the other people. And the thing is, with Beatrice, I mean, to me, it was quite astonishing that one actually is looking at Hawking effect, it was exactly 40 years ago. 50 years ago, sorry. 50 years ago that Hawking discovered, 74. And so and yet it was looked at with a fresh insights coming from quantum information, and then they could lead, I mean, under some assumptions, they were led to this conclusion that no, information cannot come out by the last ray, So I think that is fantastic. It is something that would be of interest to the outside world. So I just wanted to comment upon that and explain to the younger audience. So on the whole, I'm deeply impressed by ongoing progress on so many fronts, particularly by the diversity and intellectual breadth, clarity and rigor in thinking of the very young researchers, and also the balance between mathematical developments and applications. Of necessity, and this is a really thing for the younger researchers, of necessity, younger researchers tend to focus on one aspect of this multifaceted undertaking. But really, I would like them to keep in mind that it's utmost importance that we all follow, at least in general terms, what is happening in other areas of loop quantum gravity. Now, this is sort of the general conference that we're talking about that took place in Fort Lauderdale. But we also had yesterday an event which took place in Boca Raton, and that was Carlos' public lecture up here. And so in addition to his seminal scientific contributions that we saw during this conference, mentioned repeatedly, Carlos' tireless outreach efforts have had an enormous influence in raising the profile of loop quantum gravity all over the world. I think more than all of us, the rest of us put together, his single-handed efforts have had huge impact on Carlo is responsible for recognition of our field in the broader community and especially in the public mind. The LQG community has also benefited greatly from his involvement in the Templeton and Blauman Foundations. So thank you, Carlo, for all the energy that you have invested over the decades and continue to invest. Okay, now let me go to the second part of the talk. And this has to do with not the conference, but really in some sense future direction. And this came up just now, in fact, right? It's Eugenia's questions about testing quantum gravity, right? I mean, can quantum gravity be tested? You often hear the statement, particularly in some other approaches, that tests of quantum gravity are beyond our reach, way beyond our reach. After all, it took 100 years for tests of fully nonlinear general relativity, like through gravitational waves. The previous tests were not really for full relativistic regime. It was, post-neutron approximations were more than enough to explain them. So for forthcoming decades, we should only focus on carefully developing mathematical framework, and the test will come later. That is often a viewpoint. Indeed, I myself have said in this conference elsewhere, the test of quantum gravity through, for example, gravitational waves emitted by astrophysical black holes and neutron stars are very unlikely in the foreseeable future. For example, in the AOS and Gambini-Olmedo-Pulin models, the LQG quantum corrections to the curvature near the horizon or to the frequencies of the quasi-normal modes are way too small to have an observable effect. So, but I don't mean that that's the only place where we should look at. There's a fantastic other place, which is the early universe. It's a whole different story because the curvature at, for example, the onset of inflation is 10 to the 65 orders larger than that at the horizon of our solar mass black holes. And this opens up possibility of testing quantum gravity scenarios for the pre-inflationary evolution of the universe. I would like to briefly discuss a recent example to convey how incisive these tests can be and how sophisticated the interface of fundamental theory and observations has already become. And this is an amplification of a point that Ed already discussed, so I can be brief. But I just want to make a step back for 1 second, and people are saying, what about quantum gravity? It depends. Now, if you think about quantum gravity in a broad sense, in fact, we just had a meeting in Paris just 2 weeks ago that I was at, and we had a similar discussion, and so people asked, well, what about experimental tests? And I made the statement, no, it has already been tested. That is because when I was a graduate student, the cosmology was described in terms of perturbations which are completely quantum, which are completely classical. But now, every approach, no matter what, it could be periodic, or it could be inflationary, it could be everything. The perturbations are quantum mechanical. And what one is seeing, the density fluctuations one is seeing, these are fluctuations in the vacuum state. They are quantum field mechanical fluctuations. So, and in fact, and that there is a reasonably detailed confirmation with the experiments. So I think there's a case one can make that, in fact, these are only linearized fluctuations, but still they're quantum fluctuations, genuinely quantum fluctuations that have been seen. So these fluctuations, as you all know, is a power spectrum, and that is obtained by 2-point correlations. Again, these are quantum 2-point correlations. And so-called bispectrum is a 3-point correlation. So you get 3 modes up here, and then you take product of the power spectrum of K1 with K2, and then cyclic permutations. And then there's a numerical factor, and then there's a coefficient up here. So this is the general form of the 3-point function up here. Now, if the spectrum was completely Gaussian, then because a Gaussian has distribution does not have odd moments, and therefore this actually would be identically 0. And therefore this coefficient FNL, this non-Gaussianity of FNL coefficient up here, is a measure of non-Gaussianity. And the Planck measurements have provided a detailed first principle picture of the early universe, and the data is compatible with 0 non-Gaussianities for the observable modes. That is to say, the wavelengths in CMB that we can observe, the wavelengths which are our observable horizon size. Now, in bouncing models, particularly in loop quantum cosmology, inflationary dynamics often leads to large FNL. But this is for, so to say, modes which are even larger than we can observe, super horizon modes. Typically, they are exponentially suppressed for the observable modes. So, we say, okay, so fine. They are suppressed and they are out there. But still, because of Einstein's theory is nonlinear, there is still, interestingly, there are couplings between the observable and the super horizon modes that can leave physical effects on the observable modes. And this possibility, as first pointed out by the cosmologists, has been used by the LHC group. Francesca mentioned Ivan Aguirre's work up here, to argue that these interactions can alleviate the CMB anomalies on the observable modes. The Penn State group uses a different mechanism for alleviation of anomalies. This mechanism is not directly related to this non-Gaussianities at all, and so that mechanism has not much to do with the discussion that I'm talking about making. In other words, that mechanism stands without any controversy, but there is some issue about these non-Gaussianities. What I'm trying to communicate to you is how sophisticated these ideas are, and these experiments are. Now, since non-Gaussianities are exponentially suppressed in observable modes, one's first reaction is that they can never be detected because they would be buried in the noise. However, it turns out that given a specific model, one can use the precise predictions of that model as a template to do match filtering and dig out the signal from noise. This is exactly what is done by Lago-Virgo collaboration in their observations. And so these three cosmologists, Van Tent, Salgado, and Rudura, last year, they used this strategy with the theoretical templates of the form. FNL is some number up here times e to the minus. So these are the two parameters, alpha and n, and K1, K2, K3 are the three mores up here. Upon, this is the pivot scale of the Planck mission up here. And they use these ansatz, which is standard. It comes out in many bouncing models, and showed that bouncing models predicting n bigger than 10 to the third 3 were ruled out by Planck data. Now, these models are talking about pre-inflationary universe. So not only the inflation, but pre-inflationary, very, very quantum mechanical universe. And these actually have been ruled out. So what about LQC bounds? Well, it turns out that the absolute value of FNL does have this form, and that is well modeled by the ansatz, but FNL itself has rapid oscillations. And therefore, now what we see is not these mores, because these mores are all referred to the Fourier space, K1, K2, K3. But what we do is we take these mores, and then we project it on the celestial sphere. So we convert K1, K2, K3 into spherical harmonics using Bessel functions, and using that kernel of Bessel functions, it slightly, so to say, averages out. And we don't see macroscopically what is happening at each angle. We only see what is happening in sort of little patches, averaged out thing. And so there is a projection from the theoretical momentum space, the three-point function, into the two-sphere L1, L2, L3 of the CMB sphere, and that is what is actually observed. And because of these oscillations, this is very small comparative to the Planck data. And again, Ed mentioned this paper, Roshna and Srinath of this kind. And this illustrates that LQC, first of all, it illustrates that quantum gravity predictions can be tested, and the finer features actually matter. Just to clarify to the audience, again, because there was some discussion with Ed and Ivan during their talk, the Penn State group has elevated two anomalies, not all of them, just two of them, and that discussion just is correct, and that doesn't matter at all. Okay, so then I should just hurry up because the last part. And this is a promising path, which is really LQG at Scri+, and only at Scri+, because horizons are already talked about. Here I will continue with the discussion in Mark's and especially Wolfgang's talk. The canonical approach and spin forms have provided us with a wealth of conceptual insights and results with unforeseen physical implications, and it's very impressive that so much can be done non-perturbatively without a space-time metric in the background. We can use the rich existing results to address some of the central problems that the wider quantum gravity community is most interested in, particularly scattering theory. And the questions are, can we reproduce the interesting results that have been obtained perturbatively, and then elucidate in detail why and where the standard perturbation theory fails? How does LQG cure the ultraviolet divergences in the scattering amplitudes? Can LQG make a closer contact with the growing field of celestial holography, to which many people in the audience up here are contributing? The non-perturbative loop quantum gravity perspective is especially well tailored to the quantum nature of the Coulombic aspects of the gravitational field, as I explained in my talk on Tuesday. In particular, we have some operators using quantization of area that will be well defined in LQG, the Coulombic kind of operators. But so far, we lack a similar understanding of the radiative aspects of using the LQG non-perturbative framework. Oops. So, but there are also unforeseen, sorry, maybe it was the, okay. So the non-perturbative quantization of radiative modes in full GR has been available since the 80s. It is called asymptotic quantization that Saurath mentioned. And it provides the asymptotic Hilbert space for non-perturbative GR as well as other massless fields, including the infrared sectors. And based on connections at Scri, that is the basic variable. And since the holonomies of gravitational connection form a complete set of observables on the radiative phase space of general relativity, it is well suited for loop quantum gravity. But there are also key differences, and I think I myself had not realized it until a few months ago. namely that because Scri is a null surface, the connections on Scri constitute the full phase space. So the holonomies don't Poinsot commute. And therefore, at Scri, we cannot use a standard loop quantum gravity canonic quantum kinematics and the familiar the kinematical Hilbert space with the spin meteoric basis. There is no holonomy flux algebra, and therefore we do not have loss theorem to single out LQG kinematics. And because Scri plus is null, there are no constraints to solve. So even the basics of loop quantum gravity setup seem not to be directly relevant. And finally, in spin forms, we cannot use the boundary states from H kinematic that we have been using for the reasons I just mentioned. Given the universal structure at Scri, the internal group is ISO2 rather than SU2 or SL2C or SL2R that Wolfgang was using today. So it's ISO2. So that's the group that we have to use. But then there are also unforeseen simplifications from LQG perspective. Namely, Scri plus has a universal structure, and so therefore we have got some fields to work with in the background, if you like, that we can freely use without sacrificing the diffeomorphism covariance of general relativity. The bulk diffeomorphisms, which are identity on Scri plus, are gauge, and structures of Scri plus are manifestly invariant under this. The diffeomorphism group of Scri plus that preserves the universal structure is a symmetry group, and that is precisely the BMS group. We can use it, for example, to rigorously define mass and spin of physical fields at Scri plus in full non-perturbative general relativity. Thus, we can eat the cake and have it too. We can hope to do much of the familiar physics without sacrificing the background independence. Without sacrificing the background independence. So in this sense, asymptotic quantization scheme does not solve dynamics. This is an important point. I.e., it does not provide us transition amplitudes between Scri plus and Scri minus, from Scri minus and Scri plus. But we have spin form and group field theory for that. So what is lacking is the analog of the spin network basis, which should now be tailored to ISO2 at Scri, that interacts well with the bulk states of spin forms. With them, we could probe the S matrix from Scri minus to Scri plus non-perturbatively. As I mentioned on Tuesday, the UV cutoff provided by the quantum geometry of LQG is tailored to have well-defined operators for the Coulombic quantum observables. The older works on gravitons and loops and shadow states can be really translated to Scri and will go a long way to understand the radiative aspects from the LQG perspective. This is a promising and fertile area for the future work, and it is challenging, but yet within our reach. So with this, I just want to go to the last slide up here, which is that I was just walking up here near the river, and I saw this mural, beautiful, and it says, the clearest way into the universe is through a forest wilderness. And for me, it literally is true. It struck me, because for me, it literally is true that LQG for years has been and continues to be a beautiful wilderness that we can all explore. We have repeatedly encountered unexpected vistas in this wilderness and discovered new things. And there are a lot of treasures yet left to explore. So please, young people, do explore and do continue with LQG. Thank you.
So maybe we have time for one remark, but we should quickly leave. But does anybody want
to so in that case, a remark is mine. And, and that remark is that this has been a fascinating conference. And so I would like to thank, we already have thanked Mushin and Jonathan, but I really would like to thank the students who have worked tirelessly. I mean, particularly Jeremy has been here. He told me that he has not slept well for the whole 2 weeks period. So, I mean, I think when everything goes right, then nobody notices. When little things go wrong, everybody notices. And this is really a great credit to this whole team, led by Mushin and Jonathan, and all the students. And so really, I want to thank them, very, very much. So let's give them a hand.